Lecture 11 is about properties of distributions. We're going to look at the mean and variance of a distribution, and we're going to look at the transformation of mean and variance. The mean and variance of a random variable x and its distribution are the theoretical counterparts of the mean x bar and variance s squared of a frequency distribution. What does that mean? Well, we started our lectures looking at an experimental setup where we generated some data, and from that we calculated frequency distribution, and from the frequency distribution we had a mean and a variance. The mean and variance of a random variable and its distribution equate to that. So when we do our experiment, we get the frequency distribution from that experiment, and what we're trying to do often is to relate that to the mean and variance of the random variable that we're actually trying to measure, or that we theorize exists. So in the case of our experiment, we theorize that there is a true single distribution of the properties of the metal, which has properties mu and sigma squared, and through our experiment, by measuring x bar and s squared, we're trying to find what these values are. So the probability distribution functions and the experimental frequency distributions come together in our purpose. First of all, we can define a few characteristics of these. The mean of a distribution, for a discrete distribution, the mean is equal to the sum of all of the elements xj multiplied by the probability of each of those outcomes fxj. You add them up and that will give you the mean of that distribution. For continuous, you would do it with an integration. So we integrate from minus infinity to infinity to cover the whole possible range, and we multiply x by the probability density function dx. Likewise for variance, the variance of a discrete distribution is xj minus mu squared times the probability, and we sum those up, and the variance for continuous is x minus mu squared times the probability density function integrated from minus infinity to infinity. So for any distribution that we get, any probability density distribution, we now can calculate what its mean and what its variance are. Here's a very simple example with a discrete case. Random variable is the number of heads in a single toss of a fair coin. So this variable has value 0 if there are no heads, and 1 if there is a head. So the probability of each of those is both 1/2. So we can find the mean of this. The mean, it follows this equation. So in this case we have two possible outcomes. The outcome 0, where we don't get a head, multiply by the probability of that happening, which is 1/2, plus the outcome 1, where we do get a head, again multiply by 1/2 for the probability of that happening. So of course the mean outcome of that is 1/2. And the variance we can calculate likewise by following the equation. We put in our outcome 0 minus the mean 1/2 squared times the probability of that outcome, which is 1/2. So we do that there, and then we do the same when the outcome is 1, and that gives us the variance of that distribution is 1/4. Here's an example for the continuous case. We've got a function we've defined as a constant value k, so the probability density function is equal to a constant k in this interval, in the interval x is greater than a but less than b. Otherwise the probability density function f is equal to 0. This is called the uniform distribution in the interval x is greater than a and less than b. So we want to study this distribution, and the first question is, what is k? We've said that this is a constant value, but what is it? Are we free to have any k we want, or does it have to be a particular value? So here we've sketched the probability density function. It's a step up and then a step down. the uniform distribution. So one of the rules that we learnt earlier on is that the probability of the whole sample space must be equal to 1. So therefore, if you integrate any probability density function over the whole range from -infinity to infinity, then that must be equal to 1. That's the probability of the whole sample space. X can't be smaller than -infinity and x can't be bigger than infinity. So if we apply that condition to our function, our probability density function, then we have this. We've got the integral of k from a to b, and that must be equal to 1. And so you do that and you get k b minus a is equal to 1. So here then we can see that actually k can't be anything that we want. If a and b are fixed, then k must be defined by this expression 1 over b minus a. That must be true for fixed a and b in order to ensure that this fundamental rule is observed, that the probability of the whole sample space must be 1. So now we've done that, we can look at our mean. So the mean is x times the probability density function integrated, and so we've calculated an expression for k in our f, and so the integral is from a to b of x divided by b minus a, and we can work through that easily to find that k is equal to, sorry, that the mean is equal to b plus a divided by 2. And there we have it. So the mean is in the middle, in between a and b in the middle, which is intuitive. Then we can look at the variance of this. So we've got our equation for the variance, x minus the mean squared multiplied by the probability density function integrated over the whole range. And so we plug that in there, and this is something that we can integrate. And once you work through that integration, you will see that the variance is equal to b plus a squared divided by 12. So these are two examples, one for a discrete case, one for a continuous case, of how you can both find the mean and variance of them, and also how you can use the rule that the probability of the whole sample space equals 1 to find out certain things about that probability density function. So in this case, if you plot what that variance, what the distribution would look like, we've calculated a mean and a variance, and that's what we associate with normal distributions often. So if you plotted the normal distribution that follows that mean and variance, it would look like that. So in this case, you could say that the mean is indeed a good indicator of where the mean of the distribution is, but the variance doesn't capture the characteristics of our uniform distribution very well. So the variance is what it is, that's what it's defined as, but if you were trying to use the variance in this case to characterize the spread of that data, it wouldn't perform particularly well. So in this lecture we get to unify the experimental ideas we were looking at before with the theoretical probability ideas that we've been looking at more recently. And we had this experiment that I refer back to, and this experiment we found from our data that the mean was 873 megapascals and the standard deviation was 50.1 megapascals. And so from that we can see what the normal distribution would be that corresponds to that mean and standard deviation, and it looks like that. So when we're calculating the mean and standard deviation, we are in effect fitting a normal distribution to our data. Now we've said before that when you have experiments which involve the summation of lots of random errors, then you tend to get distributions that are normally distributed. And that's what you can see here, is that we have something that looks pretty normally distributed for the range of data, the number of data that we have. So from an experimental point of view, what we're really searching for is the true mean and standard deviation of our material property, because then that is something we can use to design equipment, to work out how thick a piece of metal needs to be, to work out when something might fail. And by doing the experiment and fitting the mean and standard deviation to it, that's giving us an estimate of what the idealized theoretical material value is. Second topic is transformation of mean and variance. So if we have given a random variable x, which has mean mu and variance sigma squared, we want to calculate the mean and variance of a transformed variable x star. And it's transformed by a linear operation, this one, a1 x star is equal to a1 plus a2 x, where a1 and a2 are constants. We call that a linear transformation. And what will happen with that transformation? What will happen to the new mean and the new variance? We'll see why this is important shortly. First of all, we're just going to work out what happens to the mean and variance when you do a transformation like this. So the first point is that if you have a small interval delta x on the original variable, then this here represents a probability of that random variable over that interval fx dx. Now when it's transformed, the equivalent region must have the same probability, and so fx dx is equal to f star of x star dx star. We can then use that when we write out the mean of the new transformed variable is x star f star of x star dx, dx star. We can then make a substitution. We can substitute in for x star using the transformation, so that would be a1 plus a2x, and we can substitute in for f star x of x star dx star, this term here, for our fx dx. And then that's an integration that we can easily do. We can take out the coefficients. If we integrate this function, it's a probability density function integrated over its whole range, and so that must be equal to 1. So we have a1, and then here we have x times fx dx integrated over the whole range. That's the definition of the mean of the function f, of the probability density function f. So that's the mean mu there. So the transformed mean is a1 plus a2 mu. So if we transform our variable by using a1 plus a2x, then our mean is also transformed to be a1 plus a2 mu. So likewise, we can look at the variance. The variance has this x star minus mu star in it. So we substitute in for x and we substitute in for mu using the transformation, and then we can see that the a1 terms cancel, so we have a2 x minus mu, and so for the variance we're calculating x minus mu starred squared, and so we can substitute in here for that, so we have a2 squared x minus mu squared f dx, and you will recognise that as being the definition of the variance of the probability density function f. And so the variance of the transformed function is equal to a2 squared times the variance of the original function. Apologies, that's an error, that should be the variance, not the mean there. So why do we do this? It's particularly important, and you'll have used this result yourself for the practice of using a standardized random variable, for example with a normal distribution. So if you've used a normal distribution, you would have used the z transformation, this one, to convert the particular problem that you have into the standard normal distribution where you have the tables of data and you can read off what the values are. So if we consider this, what we have, so x is our random variable and it's being transformed into z by subtracting mu and then dividing it all by sigma, where mu and sigma are the standard deviation and mean of our variable x. So we can just separate those out, so we have a minus mu divided by sigma term, and we have a 1 over sigma term times the times x. And so we can see that this corresponds to a1 in our transformation here, and this corresponds to a2 in our transformation. So using that, we can work out what the new mean and what the new standard deviation will be of our transformed variable z. So the mean, that's equal to A1 plus A2 times mu, the original mean. So A1 is minus mu over sigma. A2 is this one, 1 over sigma times mu. Add those together and that's 0. So this transform gives Z has a mean of 0. And then we look at the variance. The variance of Z is equal to A2 squared times the original variance. So we substitute in for A2, that's 1 over sigma. 1 over sigma squared times sigma squared is equal to 1. So this transform takes your particular variable with its mean and standard deviation, and it transforms it into a function which has mean 0 and standard deviation 1. And that's the result that you've seen so often for that, the normal distribution with mean 0 and a standard deviation of 1. And this is then something we can conveniently use to find values. So for example, let's say we have a problem, we want to find the probability that of x, of our outcome being between 5 and 7 when our probability density function is normally distributed with a mean of 5 and a standard deviation of 2. Okay, so that's what we want to find. Apologies, that shouldn't be 0, it should be a 5. So we do the transform to it, so it's 5 minus the mean, 5 minus 5 divided by the standard deviation, and then this limit is 7 subtract the mean 5 divided by the standard deviation 2. So obviously this term is 0 and this limit is equal to 2 divided by 2, which is 1. And so then we're to find the probability of this, it's the same as the probability of this. The probability that our standardized normal distribution is between 0 and 1 standard deviation, and then that's something that you can find from tables very easily, and it's 0.34. So to summarize, we've looked at our properties of distributions, and we've looked at how you find their mean, how you find their variance, and you've seen how if you integrate a probability density function over its whole range, it must always equal 1. So you can use that to check that they are scaled properly. And we've looked at the transformation of mean and variance, which enables us to use the Z transform, for example, which is what we use to find probabilities of normal distributions. So the next lecture of this section of this week is going to just take a look at a few common distributions, the binomial distribution, the Poisson distribution, and a log normal distribution, to see how we can use, or to see how common problems can be represented with these distributions and how we can start to use them to solve some engineering problems. Thank you.